Pause the video, give this a go yourself first. Okay. So we've got this diagram here, we need to label it. A would be your general purpose registers. How can I tell? Well, here's the thing. You've got your main memory here, your RAM. All these arrows are going towards A, which would be registers like your MAR, your MDR, etc. So therefore it tells me that the RAM is connected to A, these registers, via D, E, and F, which we'll talk about in a second. So they'll be my registers, my general purpose registers. We've got something from here going into the control unit. Let me just knock this off. It's not going to be a control bus, it's not going to be an address bus, it's not going to be the ALU, it's not going to be secondary storage. Secondary storage we're going to eliminate straight away. It's not part of this diagram at all, we know that, because secondary storage has no real relationship with the CPU, it goes through the RAM. So then that leaves us with the system clock, which the control unit uses for its signals. We then have a relationship between the control unit and C. Well, this would be the ALU. Why? Because it will be the control unit which simply, where it decodes, work with the ALU and whatever's inside of the ALU to perform the calculations and logic. It's given us D as being a data bus, so therefore that would have made A really easy. The data bus goes from RAM all the way to the MDR, i.e. a general purpose register. E, which is here, we can see that we've got an arrow here and it goes in both directions, and it's also connected between the RAM and our registers. That'll be the control bus, which is responsible for the signals within the CPU and the components which work with the CPU. Finally, we have F. Now, appreciate that this is drawn slightly differently to what I would expect you to understand from F, because F is the address bus. But the address bus is unidirectional. It's drawn here where you've got an arrowhead and an arrowhead here, which breaks conventions. We're trying to display that this whole system is bidirectional by its very nature. However, for reference points, F is the address bus. And you'll notice that there's an arrow from the control unit to the address bus. That's basically sending signals for the address bus to go and fetch the next, go to the next address location in the RAM, which is why we've got this arrow here. We then have clock speed as a factor that affects performance of a PC. Explain this statement. Well, here's the thing. The way clock speed works is that it sends out a number of pulses in a given time. That's how clock speed works. So it's like, imagine like a heart beating. Boom, 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 boom. And here's the thing. Each instruction takes a certain number of clock cycles to execute. So appreciate that instruction will be broken down to different processes. So imagine that we've got one instruction which looks like this, and let's say it was to, I don't know, load, I'm making this a really abstract game, and let's then imagine that it's split into individual jobs or processes. process 1, process 2, process 3, process 4, process 5, and process 6. This goes into the fetch code execute. This then will go into the fetch code execute. This will, and then this will. Once they've all been executed, this instruction has been done. Now, this may take quite a bit of time because there's quite a few processes. So it's going to be obviously more than one fetch the code execute cycle to do this. Keep that in mind for now. I haven't mentioned anything about the advantage of increasing clock speed yet. All I've said is clock speed is the idea that it sends out a number of pulses in a given time. Each instruction will take a number of clock cycles for it to be executed completely. Now, the higher the frequency, so the higher the clock frequency, as in the more pulses, the shorter time for execution. So if we go back to this one instruction split, instead of it going it's going to go it's going to get executed faster. This basically means that performance increases. Pause the video, give these questions a go yourself first. Okay, so we've got register transfer notation, which is basically shorthand code to show the flow of how a CPU works. Now, if we're going through step by step, let me just draw out the way I would do a CPU, which would be the program counter, then you have the MAR, then you would have the MDR, then you would have the CIR, mail space, and then you would have the ACC, which, let me just move this down, that's a good idea. It's in the ALU, you've got the control unit here as well. You've got main memory. So step 1, we have program counter, which copies the address location to the MAR. The MAR then has the address bus for the fetch. It comes back the data bus, drops it off in the MDR. MDR copies value to CIR. CIR get the codes. Okay, so let's have a look at our transfer notation. This is saying program counter, put it into the MDR. That is not what happens. So line error 1 is incorrect. It should be program counter going to MAR. Now you'll notice that I'm using brackets here, and I'm using brackets, well, I'm not using brackets, should I say, on the MAR. The brackets doesn't mean it's a register. That isn't what we're saying. We're saying about the contents in that register. So we're saying we're going to take the content, the data, the address location of whatever's inside a PC and put it into the MAR register. That's what we're saying. Line 2, program counter goes up by 1. That is fine. The program counter will go up by 1. It will increment. We're then saying on line 3, we're going to take the contents of the MAR and put it into the MDR. Well, we know that it goes from MAR, and we need to get the contents first from the RAM, the main memory, and then the data bus puts it into the MDR. So that's an issue, and I'm going to explain why now. I'm going to put MDR here. That is correct. It's also correct that we want to get the contents of the MAR and put it into the MDR. That's fine. But we also need another bracket, and this is representing the process of having to go to the RAM to get the instruction, to get the data. Once it gets the data instruction, it then puts it into the MDR. So that's two things the MAR is responsible in terms of storing data. It stores the address, and you could argue in this situation, because we're skipping out the buses, is responsible for the data / instructions, which are being fetched, and then it goes into the MDR. line 4, it says program counter CIR. Now, here's the thing. There isn't a direct relationship between the program counter, which is over here, and the CIR, which is over here. It's the MDR, which puts a value into the CIR. So that's an issue. So we've got CIR, and this should be, in square brackets, the value inside of MDR. And there we go. This next question, it's very easy, it's just about buses again. So, address bus, we know is unidirectional. We know that a control bus goes in 2 directions, and we know the data bus goes in 2 directions. Pause the video, give us a go yourself first, and then I'm going to do a lovely solution. Okay, so this is similar to the previous question we looked at. We need to do we actually need to draw out the register transfer notation ourselves. So, memory address register stores an address. The contents of this stored address are copied to the MDR. Cool. So we've got the MDR is the receiver, and it's going to get data from the MAR. Now we know that the MAR has the address data, and we know that it then has to go to the RAM to fetch the data instructions. So it's like that. Contents of the program counter are then copied to the MAR. So we've got the MAR here, and we've got the program counter here, and we need to put it around brackets because the contents. The contents of the MDR are copied to the CIR. Easy. CIR, MDR. And finally, incremented contents of the program counter. So it's program counter equals program counter plus 1, and then let's put this in brackets, just like in programming. The next question is we need to put this in order of the fetch, decode, execute cycle. So what is step 1? Well, step 1 would be B. That would be step 1. I'm then going to say step 2 is going to be A. D can happen at any point after this step here, after step 1, as in the program counter going up by 1. So I'm going to do it here. D. I could have put it here instead. I could have put it here. And finally, obviously, we're left with C. Down below, we've got our buses again. Buses are used to transfer data between various components of the computer system, receives data from the MAR, so that'll be address bus, carries an address or instruction value, that's going to be a data bus, transfers timing signals, that's a control bus, and it's bidirectional, control bus and data bus. Pause the video, give these questions again yourself first. Sorry about that. Okay, so we're dealing with registers. What is a register? Well, a register is something which works memory that stores something. That's a register. Now, we appreciate that there's special purpose registers, and we write the word special down here. And we've also got what's known as general purpose registers. We'll talk about those in a second, but first of all, what is the role of the MAR? Well, whenever we talk about registers, we talk about store. So it stores the next address to be fetched. That is its role. It's held in the program counter, then passed to address bus that fetches from memory. We then have the MDR. Again, stores, but this time data from address, location, pointed at, or should I say pointed to, by VMAR. So if you think about it, keeping it really simple, if we've got 0001, so address location 1, that's inside VMAR. We go to address location 0001. We then get the data from here, blah, 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 and we put it into the MDR. The data then is copied to the CIR. I've got this habit of writing letters with missing out the middle letter. I don't know why I keep doing that. Anyway, now I'm going to talk about general purpose and special purpose. It's really simple. General purpose can be used for many different functions. So this is where we're talking about things such as the ACC. Because the ACC can be used for different operations. So the ACC can do things so it can deal with different types of calculations, but also logic as well. So it can be used in different contexts in different ways. It could also be used as temporary storage. Therefore, it's general. It doesn't have one specific job. Special purpose registers are things such as the program counter. It's got a specific job. The CIR, one specific job. But you've also got registers such as the status register, and you've also got the interrupt register. I'll talk about the interrupt register and the status register when I look at interrupts. But they do have one specific job. They're special in reality that they're unique. They do that one job and that one job only. They can't be cloned by anybody else. Pause the video, give this question a go yourself first. Okay, so again another similar question, different style diagram. Let's work this out. Let's start with A. We can see that there's a line going to the control unit, so we know we're dealing with a control bus. That's easy. See what I mean? I keep missing out letters. Okay, let's now go to B. This time on this diagram, it's unidirectional. Goes to the RAM, so we know we're dealing with the address bus. Which means the next one is data bus, and we can prove that bidirectional registered main memory. Okay, we're now back to our what does this register do? Stores, 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 and stores. Okay, so what does the program store? Address of next instruction to be fetched and executed. Stores the data between memory, as in the RAM, and other registers, then passed to CIR to be decoded / executed. CIR stores current instruction to be decoded / executed, and the address register stores address memory location that needs to be accessed to be fetched. Well, it needs to be accessed, let's say, so instruction can be fetched. Pause the video, give us a question you go. Redo. Pause the video, give us a go yourself first. Okay, there's 3 questions here. Okay, let's do the register question first. Current instruction register stores the data that's just been read, stores the instructions that has been decoded and executed. Decoded, CIE, perfect. There's a match. Memory address register stores the data that has just been read. No. Stores the address of the input. No. Stores the address of the next instruction to be read, potentially. Stores the address of the memory location about to be written to or read from. Yeah. So to put it into layman's terms, I'm going to explain the difference between the program counter and the MAR's definitions here. So we've got obviously the program counter, which is linked to here. How did we know that this bottom one is MAR and this one is for PC? Well, the role of the program counter is just to store address of next instruction to be executed or read. That is the job of the program counter. MAR at times will do the same. So this will be exactly the same, so I can just like copy and paste this into here. But also the MAR doesn't need a program counter sometimes, because it could also store address location for us for writing to memory. Let me explain. I'm going to make it in a really concrete example way. We've got our program counter, we've got our MAR, we've got our MDR, we've got our CIR, we've got our ACC. Let's imagine that the ACC in a game has made our lives go up by 1. So we've got an extra life in the game. Lives equals lives plus 1. We've got our RAM over here. We've got address locations. Let's imagine that in address location 1, we fetched our lives. So we fetched the current lives, which was 3. So we fetched lives equals 3, lives equals 3. Our instruction is make lives go up by 1, so we're now going to have 4 for lives. We now want to update our game. So we're going to pass this back. Inside the MAR is still the address location 1. This PC may have gone up by 1 to 2 to fetch the next instruction, but in the MAR, it's pointing to 1 still. That will allow us to write back to find the location and update our lives to make it 4. So therefore, the MAR is allowing us to store the address location of data to be read from, which is where we're fetching, or written to if we want to update the contents. That leaves us with MDR, and MDR stores the data that has just been read from memory or about to written to memory. So goes back to this again. MDR can take data from here and put it into here, so we just read it, so we're just about to execute, or we've updated it in the ACC and we're passing it back into the RAM, so read or written to. Our next question, 2 other buses that exist apart from the address bus, where we've got data bus and control bus. Data bus carries data between CPU or processor and memory, whilst the control bus transmits signals between control unit and other components. This final question. So I want you to picture let's just erase this. We've got the Cayman Islands, which is a small island in the Caribbean. They have buses, but they're like mini buses. You can fit about 8 people in them. In England, you've got double-decker buses. Let's say you can fit 200 people in them. 200 people versus 8. Imagine that we were to increase our address bus from 16 people to 32 people. What's going to be the benefit? Well, if we can have more people, or potential people, that means we can have more address locations. That's the point of the address bus. It stores memory address locations. The more wider it is, the more memory address locations we can store. So what's the benefit? Let me give you the answer, and I'm going to put the answer here. By doing this, we're going from 16-bit, which we can say is 2 to the power of 16, 2 being binary, base 2, 16 mal bits, to 32 bits, to the power of 32. That is going to allow us to increase the number of addressed memory locations that that the bus can directly access. So I put that as my answer. I'll mention this, I'll mention this, and then I'll talk about this. Pause the video, give this question a go yourself first. Okay, so we're talking about interrupts. What can generate an interrupt? Well, we've got different things. We've got a hardware interrupt, or I'm going to put hardware fault. You've got an input-output request. You've got a software error interrupt, or you've got end of time slice. Let me just talk about each one of these really quickly. So a hardware fault could well be something as simple as like your CPU overheating. CPU overheating, it's got a sensor in it. What it'll do, it'll tell the operating system to shut down. So your computer will shut down automatically. That basically creates an interrupt. Input-output request, me just pressing a key on my keyboard, like the start menu key, has created an interrupt. You then got software interrupt, which is normally to do with when we've got errors in code. So let's imagine I wrote some code and I'm trying to divide by 0, which is impossible mathematically. But let's imagine I accidentally had that in my code. It would cause a crash. It would interrupt my program, and it'll cause the operating system to close down the program. So the OS closed down the program I was making. We then have time slice. Basically, in your computer, you've got, let's imagine that this was a job queue. All of these things I've got open. I've got Spotify, I'm playing music, I'm recording a video, so I'm using recording software. I've got this whiteboard software. I've got Google Chrome. I've also got Discord. My CPU can only deal with certain things at a time, so it's going to deal with Spotify. It'll then deal with my recording software, then my whiteboard software, then Google Chrome, then Discord. if it does it in order like 1, 2, 3, 4, 5, and it gives everyone like 10 seconds of attention. Spotify, I'm going to give you 10 seconds. Recording software, 10 seconds. Whiteboard, 10 seconds. Chrome, wait a second. Discord, and it just goes around like that. We call that round robin. Once that 10 seconds is up, the recording software will interrupt the CPU and say, yep, it's my turn now. After 10 seconds, the whiteboard will be like, yo, it's my turn, so I'm going to interrupt. And that is literally another way things can be interrupted. But why do we have interrupts? Well, it basically allows our computer to multitask. It allows us, the CPU, to deal with different processes working with the operating system to allow that all these processes get their attention. So it allows multitasking. It allows our computer to run efficiently, effectively. That is why we need interrupts. Without interrupts, we can't multitask. Our computer can't run effectively. We'll just have to deal with one job at a time. It'll just deal with Spotify and Spotify alone without looking at these other processes which needed attention as well. So 3 different events that can generate an interrupt would be any of those: hardware fault, input-output request, software error, or end of a time slice, which is what I talked about here. Now we're going to talk about how the interrupts actually run.